Welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here. Hit the notification bell below. You'll get notifications for this series and a bunch of other ones on our channel. Today we're doing multivariable calculus. This is chapter 3, vector calculus, and we're doing 3.6, which is parametric surfaces. This lecture we're going to do parametric surfaces and their surface areas. Let's do that. All right, I found a kitty. This is Jasper. We're going to do the parameterization of a plane P through a point x naught, y naught, z naught containing two vectors A and B. Okay, you go do that. I'll do this. So what we have, first of all, always, just like Mark's alma would always say, draw a picture first. I have a plane P. I have a point P naught. And then we can pick an arbitrary point P, which is, P is going to be x, y, z. Then we have two vectors, B and A. What we're going to do with this scenario is we're going to create a parametric equation for the plane through the point P naught and containing vectors A and B. That gives us specifically, if I create this vector now, which we're going to call R minus R naught, what we notice is it is laying in the plane, so it is a multiple or a linear combination of A and B. And what that means is I'm going to have U times A plus V times B for some parameters U and V. Or in particular, and this is going to be viewed as a vector, R is going to be 0, the origin P. So we have an origin over here somewhere. So it's this vector we're actually creating, R, and then R naught. This is linear algebra, of course. But what that gives me is R is equal to R naught plus UA plus VB. This is the vector form. Specifically, what we're going to do with that is that gives us a parameterization R of UV is equal to, what were the coordinates of R naught? That's x naught, y naught, z naught. So that's going to give me x naught, y naught, z naught plus U times scalar multiplied A1, A2, A3 plus V times scalar multiplication of B1, B2, and B3. Once I have that, I use scalar multiplication and addition of vectors, and I get our parameterization of this plane, which is our surface, which is going to be R of UV is equal to x naught plus UA1 plus VB1, comma, y naught plus UA2 plus VB2, and z naught plus UA3 plus VB3. This is the parameterization of that plane. Now let's do a specific example. We'll give you a plane containing a point and two vectors, and we'll give this specific parameterization description of that plane. All right, as a specific example, given a plane P containing these points, P, Q, and R, let's find the parameterization of that surface. What that's going to give us, first of all, I need two vectors, A, which is going to be PQ, which as vectors is Q minus P, which is going to give me 2, 1, 1, minus 1, 2, minus 1, which is going to be 2 minus 1 is 1, 1 minus 2 is minus 1, and 1 minus minus 1 is 2. And then B is going to be PR. First of all, you should be drawing yourself a picture. I have a plane P. It contains P and Q. You can draw it here, Q and R. I'm going to draw these two vectors. That's going to be A, that's going to be B. Once I have that in mind, then I'm creating those vectors. This is going to give me R minus P, which is going to be R as a vector, minus 1, 1, 0, minus 1, 2, minus 1, which is going to be minus 1, which is negative 2, 1 minus 1, 2 is minus 1, and 0 minus minus 1 is 1. Now I have my vectors a and b. What I have to do is create the parameterization of that. That tells me that r of u, v is going to equal one of my points. So any one of these, 1, 2, minus 1, plus u times a, 1 minus 1, 2, plus v times b, negative 2, negative 1, 1. So that gives me r of u, v. My parameterization of this plane is going to be equal to 1 plus u minus 2v, comma, 2 minus u minus v, comma, negative 1 plus 2u plus v. Now let's look at considering the surface area of these parameterized surfaces. All right, for the surface area derivation, what we've got is a surface over a region D. What we're going to do is choose a point, and then just as we did earlier in this series, when we talk about a tangent plane at a point, we're going to fix u equal u naught and then v equal v naught. We're going to get two tangent vectors. The tangent plane containing those are now going to contain the vectors ru and rv. When we look at all these sub areas, the surface area of those sub rectangles are approximately going to equal the area of the tangent parallelogram. Those tangent parallelograms are equal to a cross product which contains these vectors delta u r, or sorry, that should be delta v, delta v rv, and delta u ru, multiples of these vectors in that tangent plane. And that gives us an approximate surface area of the norm of ru cross rv, delta u delta v, and that gives us the double integral over d of the norm of ru cross rv dA. Let's try an example of that. All right, let's find the surface area of this paraboloid z equals x squared plus y squared under the plane z equals 4. Let's draw a picture quickly. There's our surface. Z equals 4 is right here. That's going to give us this paraboloid x, y, z. And then we want the surface area of this thing. And so what we're going to do is parameterize this. First of all, what I notice is I'm going to let, because we have x squared plus y squared, that I'm going to let x equal r cos theta and y equal r sine theta. And then what that means is z is going to equal x squared plus y squared, which is r squared. Then I have my parameterization. R of r theta is going to equal r cos theta, r sine theta, r squared. Then what I need are the two partials. I need to compute the partial of this vector with respect to r and theta to get, and then get the cross product and get their norm, and then we can compute using the differentials. Then what we're going to get is, this is going to give us r of r, unfortunately, is going to equal cos theta sine theta 2r, and then r theta is going to equal negative r sine theta r cos theta 0. Then what I need is their cross product. That says their cross product r cross r theta is going to equal I j k, which is now what? Cos theta sine theta 2r, negative r sine theta r cos theta 0. That is going to give me, I'm going to get 0, and then negative 2r squared cos theta I, and then minus, in j, I'm going to get 0, so 2r squared sine theta j, and then in k, we're going to do block, block, and I'm going to get plus r. Yes. Okay. What does that give me? That gave me the vector negative 2r squared cos theta, negative 2r squared sine theta, r. Then I need the norm of that. The norm of r cross r theta is equal to the square root of 4r to the 4 cos squared theta plus 4r to the 4 sine squared theta plus r squared, which is equal to the square root of, first of all, I've got r squared that I can pull out, and that's going to give me 4r squared cos squared theta plus sine squared theta plus 1. If I factor everything out carefully, and that is going to give me r times the square root of, this is 1, 4r squared plus 1. That means that dA is going to be the norm of r cross r theta, dr d theta, which is going to be the square root of 4r squared plus 1 r dr d theta. Now let's move that up and put it into the surface area formula and compute the surface area of that paraboloid. That says that the area of the surface is equal to the double integral over the region D of the norm of r cross r theta dA, which we just found was, and sorry, we noticed that 0 is less than or equal to theta is less than or equal to 2 pi, and 0 is less than or equal to r is less than or equal to 2. And therefore, we have that this is the integral from 0 to 2 pi. The integral from 0 to 2 of this was the square root of 4r squared plus 1 r dr d theta. I can split this. This is equal to the integral from 0 to 2 pi d theta times the integral from 0 to 2 of the square root of 4r squared plus 1 r dr. This one is equal to 2 pi. This one I have to use substitution. W is equal to 4r squared plus 1 over 8. dw is equal to r dr. And then we're going to get that is 1 over 8 times 2/3 w to the 2/3. I'm just going to put that back in. 4r squared plus 1 to the 3 over 2, evaluated from 0 to 2 using that substitution. And that is equal to, canceling this, I'm going to get 4. We're going to get these 2's and the 8 cancel to give me pi over 6. And then in here, evaluating at 2 and 0, I'm going to get 17 root 17 minus 1. Please subscribe right here, hit the notification bell. I'll see you next time.